Hello everyone, today we are going to do the 12th lab of digital signal processing. In this lab we are going to design the IIR filter, which is infinite impulse response filter. So moving to the task 1, this task we have given the sampling rate of 8000 Hz and we are going to design second order Butterworth filter. So here we are going for the second order equation, which is this, and then we are converting to digital filter using bilinear transformation. Then we are plotting the magnitude and phase response by using the frequency Z command, which is the built-in command, and we are labeling X and Y axis and with the title magnitude response of Butterworth low pass filter, and we are also creating a new figure for phase response. So when we run this code, we have the output like this. This is the magnitude response of the Butterworth low pass filter, and this is the phase response of the filter. Here we can also see the phase response of Butterworth filter. Now moving to the second task of this lab. Let's close this. In this task we have given the numerator, which is 1 1, and the denominator 1 and minus 0.5. This is the transfer function which is given. We are going to find the impulse response, step response, and the system response. We have the input signal which is varying from 0 to 10, and then we are plotting its result. First we are plotting the impulse response, then we are plotting step response, and at the end we are plotting system response. We are using the subplots command here. So the purpose of subplot is to plot all the graph in one figure. So when we run this code, this is the impulse response on the top, then we have the step response, and at the end we have the system response at the end. Now moving to the next task. In this task we are plotting the pole and zero diagram of the system. The given system is 1 minus 0.5, and in the denominator we have 1 1.5 and 0.45. We are using the transfer function built-in command TF of MATLAB, and then we are plotting its pole and zeros and the frequency response. So when we run this code, so first we have the frequency response, then we have the phase response, and this is the pole 0 diagram of that system. As you can see, we have pole 1 at about minus 1, and the other is at minus 0.4, and 1 0 we have at about 0.5. Now moving to the next task. We are going to design the filter with the given coefficient 1 in the numerator and minus 0.5 in the denominator. We have the sampling frequency of 8000 Hz, and we are computing the frequency response up to 1024 points. We are using the frequency Z command, which is for the frequency response of the system, and it is the built-in command of MATLAB, and then we are plotting its magnitude and phase response. So when we run the code, we have the output like this. We have first the frequency response, and then we have the phase response of the system. Now moving to the next task. This task we are again defining a filter, which I have given a transfer function, and then we are plotting the pole and zero diagram here. Then we have frequency response calculating using the frequency Z, which is the built-in command of MATLAB, and then at the end we are plotting the magnitude and phase response, and then we are identifying which filter type based on frequency response. If max ABH is equal to 1, then it is the all pass filter. If it is less than 1, then it is the band pass filter, as it is a low pass filter. Else if min absolute of H is greater than 1, then it is a high pass filter. Else it is a band stop filter. So when we run the code, it will identify what kind of filter it is. So here you can see the filter is being identified as a band stop filter, which we can verify from the frequency response here. Now moving to the next task. In this task we have given the two filters. Filter 1, which is in the numerator, which has given 001 and the denominator 1 minus 1 by 2 1 by 3 and second filter is respectively. First we are calculating the transfer function of both of these filters, then we are plotting the pole and zeros for these filter, and then we are comparing the result of both of these filters. So when we run the code, so let's zoom the picture. This is the pole zero diagram of both of these filters. As we can see, the poles of the filter 1 are in the imaginary axis and the poles and zeros of filter 2 are on the real axis. Now moving to the last task of this lab. In this task we are again defining or designing a second order Butterworth filter. We have given the sampling frequency of 8000 Hz, then we are plotting the magnitude and phase response, and then we are creating a new figure for phase response. So when we run this code, so this is the phase response of Butterworth filter. This is the magnitude response of Butterworth low pass filter. So this is all for the lab 11. Thank you for watching. Lab 12, sorry. Thank you for watching.